Hi everyone, I am Dr. A. Prasanna, working as Assistant Professor in the Department of Chemistry, V.V. Vanya Perumal College for Women, Virudhunagar. In the last video, we have seen the types of organic reaction which includes substitution reaction. So in continuation of that, in this video, I am going to deal with aromatic electrophilic substitution reactions. Let me recall the substitution reaction. The substitution reaction is the reaction in which one or group of atom from one reactant is to be substituted with the another atom or group of atoms from the another reactant. That may be called as the reagent. That may be from the reagent. This electrophilic substitution, actually the substitution reaction is of two types, that is it may be nucleophilic substitution reaction or electrophilic substitution reaction depending upon the attacking reagent. In this video we are going to focus on the electrophilic aromatic substitution reaction, that is the attacking reagent is the electrophile. It attacks the aromatic system, specifically the benzene ring. So this is the benzene system. Here the electrophile attacks the benzene system, benzene ring, to form a substituted product. So this is an example for electrophilic substitution reaction. Here this reaction is brought about by an electrophile. Generally we can call that as E+. Depending upon the electrophile, this may be of halogenation, that is here this benzene ring has a hydrogen atom. This hydrogen is to be substituted by halogen X. This type of reaction is halogenation, or if the reaction is brought about by the NO2 group, H is replaced by NO2 group, then that is said to be nitration. It may be of sulphonation, that is H atom is replaced by sulphonic acid group. Also this electrophilic substitution reaction includes Friedel-Crafts alkylation and Friedel-Crafts acylation reactions. In alkylation, this hydrogen atom is replaced by the alkyl group. In acylation, the hydrogen atom is replaced by the acyl group or CO, acyl group. Then we are going to see the general mechanism of the various types of electrophilic substitution reaction. The general mechanism covers the different steps. In the step 1, an electrophile is generated. That may be in presence of catalyst. In the presence of catalyst, the attacking reagent generates an electrophile E+. In the step 2, this generated electrophile attacks the benzene ring and forms a stable, resonance stabilized carbonium ion. We may call that as sigma complex. Here this carbonium ion is resonance stabilized, and this intermediate can be written as a hybrid as sigma complex. The resonance structure is focused here. So this is this carbonium ion is involved in resonance. These pi electrons may move in order to neutralize the burden created by the positive charge at the carbon atom. In the third step, loss of proton gives the substitution product. So this is the stable carbonium ion generated. This upon loss of proton leads to the formation of the desired product, substituted product. This is the general mechanism for all the types of aromatic electrophilic substitution reaction. So let me focus one by one all the types of reactions. Let us see halogenation of benzene. So let me point out the overall reaction first. So the overall halogenation reaction is that benzene reacts with chlorine in presence of catalyst ferric chloride and forms the product chlorobenzene. This chlorobenzene is the substituted product here. This is the overall reaction. When we look into the mechanism, in the first step, the attacking reagent, that is chlorine, forms an electrophile in presence of catalyst ferric chloride. So this Cl2, that is the attacking reagent. This attacking reagent in presence of ferric chloride forms, this is chloronium ion. Chloronium ion. This is the electrophile. Electrophile is nothing but electron loving species. It can attack at the nucleophile, that is benzene ring here acts as a nucleophile. Because of the pi electron cloud above and below the plane of the benzene ring, it can act as a nucleophile for the electrophile. In the second step, the chloronium ion formed in the first step attacks the benzene ring, leading to the formation of the carbonium ion. This is resonance stabilized carbonium ion. In the third step, this carbonium ion loses a proton, leading to chlorobenzene. The chlorobenzene is the desired product. When we use the attacking reagent as chlorine in presence of ferric chloride, chlorobenzene is the desired product. This halogenation can also be done in presence of bromine. Here attacking reagent is bromine. So when this attacking reagent generates electrophile, that is said to be bromonium ion, Br+. That Br+ attacks the benzene ring and forms the product bromobenzene. So in general, halogenation, we can say X2 in presence of catalyst ferric halide. Let me switch over to the next type of aromatic electrophilic substitution, nitration of benzene. Let me point out the overall reaction of nitration. Here, benzene reacts with concentrated nitric acid in presence of concentrated sulfuric acid. When it is heated to 60 degrees centigrade, the substituted product, that is nitrobenzene, is obtained. Here, nitro group gets substituted at the benzene ring. One of the hydrogen atom in the benzene ring is replaced by the nitro group, NO2 group, generated from the mixture of concentrated nitric acid and concentrated sulfuric acid. Let me point out the mechanism for this nitration of benzene. As usual, in the first step, the formation of the electrophile, NO2 plus electrophile is generated from the mixture of concentrated nitric acid and sulfuric acid. This NO2 plus, we can call that as nitronium ion. This nitronium ion is the electrophile. This is formed in the step 1. This electrophile attacks the benzene ring and forms a resonance stabilized carbonium ion. So this resonance stabilized carbonium ion, that may be called as a sigma complex. In the third step, the loss of proton of this carbonium ion leads to the formation of the nitrobenzene. Look at this. Actually, the loss of proton, H plus is removed here. This bond shift here. So this positive charge is compensator. Double bond is generated there. Okay, so nitrobenzene, that's the substituted product, is formed. Let me switch over to the next type of aromatic electrophilic substitution, that is sulphonation of benzene. From the name itself, sulphonation is the substitution of hydrogen atom at the benzene ring by the sulphonic acid functional group, that is SO3H. The overall reaction may be given as benzene with concentrated sulfuric acid, or we can use this fuming sulfuric acid also. When we use these two different reaction condition, it forms a substituted product, that is benzene sulphonic acid. Benzene sulphonic acid. So that is a fuming sulfuric acid is nothing but it's a concentrated sulfuric acid which contains added sulfur trioxide, SO3. Okay, this is the overall reaction. Mechanistically, we can say in the first step, from the reagent that we have added, electrophile SO3 is generated. Look at this. These are the other two ionic products that is involved in the next upcoming steps. This is hydronium ion. This is HSO4 minus, hydrogen sulfate ion. In the second step, this SO3, this is the neutral electrophile. In the previous cases, we have seen in the previous case, we have seen positively charged, that is electrophile. Here, this is neutral electrophile. This has no charge at its center, but the sulfur behaves as an electron deficient center. So this can act as neutral electrophile here. So this SO3 attacks benzene ring, leading to the formation of the carbonium ion. This carbonium ion is resonance stabilized, that is, it may be called a sigma complex. In the third step, loss of proton leads to the formation of sulfonate ion. This is the substituted product in the ionic stage. This, upon addition with proton, it forms benzene sulphonic acid. So SO3H. In this place, H plus gets added. It is obtained. This H3O plus and HSO4 minus, these two ions are from the step 1. So in the step 3 and step 4, that will react, leading to the formation of the product. Okay, so this is the benzene sulphonic acid. Look at this. Instead of one hydrogen in the benzene, sulphonic acid functional group gets substituted. So this is sulphonation of benzene. This reaction is carried out in presence of concentrated sulfuric acid, or we can use fuming sulfuric acid. The fourth type of reaction that we are going to see is Friedel-Crafts alkylation of benzene. So from the name itself, in the benzene ring, one of the hydrogen atom is replaced by the alkyl group. Generally, we can call that as R. The overall reaction is benzene reacts with alkyl halide. For alkylation, we are using the reagent alkyl halide. From this alkyl halide only, electrophile is to be generated in presence of the catalyst aluminium chloride. So here the product obtained is toluene. Depending upon the attacking reagent, the substituted product may vary. If you take alkyl halide, that is methyl chloride, the substituted product obtained here is toluene. Okay, that CH3, in general we can call that as R. If you take that R as methyl chloride, H is replaced by the methyl group. So benzene with the methyl substituted product, that is said to be toluene. Okay, this is the overall reaction. When we look into the mechanism for this reaction, in the step 1, electrophile is generated from the attacking reagent and the catalyst. So this is the attacking reagent, CH3Cl. From this methyl chloride, CH3 plus, this is the electrophile, electron loving species, that should be positive in nature. So this is the electrophile generated in the first step. This electrophile in the second step attacks benzene ring, leading to the formation of the carbonium ion. So what is carbonium ion? Carbon with positive center. Okay, so here the substituted methyl group is here, adjacent to the substituted group, carbonium ion, that is carbon with positive charges here. This is resonance stabilized. In the third step, loss of proton forms a desired product, that is alkyl benzene. Okay, so this H plus is removed. This bond shifts here. So new double bond is generated. That positive charge is compensated, or we can say neutralized. Toluene is obtained. From benzene, we have synthesized, we have prepared toluene by using Friedel-Crafts alkylation. The last type of aromatic electrophilic substitution is Friedel-Crafts acylation of benzene. From the name itself, acyl group is to be substituted instead of one hydrogen at the benzene ring. So here the attacking reagent is acetyl chloride. Acylation, the attacking reagent is acetyl chloride. The catalyst used is aluminium chloride. So the product formed, the substituted product formed is acetophenone. Acetophenone is a ketone. So ketone functional on one side, benzene phenyl ring is there, another side methyl group is there. So this is acetophenone. We can prepare acetophenone by Friedel-Crafts acylation reaction by taking benzene with acetyl chloride in presence of aluminium chloride. Okay, so this is the overall reaction. Mechanism, when we look into the mechanism, in the step 1, as usual, electrophile is to be generated. So here attacking reagent is acetyl chloride. From acetyl chloride, this acyl radical, it's not radical, it is carbonium ion. Or we can say here this one is electrophile. Acyl electrophile is obtained. Okay, in presence of the catalyst aluminium chloride. In the first step, this electrophile is generated. In the second step, this electrophile attacks the benzene ring, leading to the formation of the carbonium ion. In the third step, the loss of protons, the loss of proton gives the aromatic ketone here. Okay, what happened here? Just in the benzene ring, one of the hydrogen is replaced by the acyl group. Okay, so here acetophenone is obtained. Okay, we have today seen 5 different types of aromatic electrophilic substitution. Number 1, halogenation. Next, nitration. Third, sulphonation. Fourth and fifth, Friedel-Crafts reaction. Fourth is the alkylation reaction. The last type we have seen acylation. Friedel-Crafts alkylation and acylation, both reactions we have seen. Up to this we have seen the aromatic electrophilic substitution reaction. Thank you.